just make sure this is gonna go live, and then we can get going. Things are looking good on the live stream, so we're doing good. Hope you're doing okay today, and I'll just wait for this thing to hit. Awesome. Today, going to be going over direct I2C access in your Zephyr code. Because there are I2C APIs, why not? So we're going to do it a little bit more of a conventional way that many of you have used to get your I2C communications, just write and read, things like that. Go over a quick demo of just that code being used. I've also included a link to that in the description box below, so you can check it out. But we'll kick this off and get going. But first, if you haven't already, please hit the thumbs up, subscribe, leave a comment, and let me know about the things that you'd like to see me cover on these live sessions. They're every week, and most of the topics are ones that are inspired by the community, so including this one. And we're gonna just keep on rolling. So thank you for being here, and yeah, I'm just really excited to keep going with this. All right, let's go. Question of the moment today is, could you make a video setting up I2C on NRF 9160 Feather? And of course I can. I'm going to make this a little bit more generic, but it should, so it can apply to everything, but you can kind of get the idea. So direct I2C, yes, it's possible. Don't have to say no on this one, just because many of the drivers for Zephyr, yes, they use this API to get there. So there's no reason why you couldn't be able to use it in your own application or whatever, if you have to do maybe some very basic things, or you don't really care for, or maybe the APIs that Zephyr provides for any sensors is just not sufficient for your device. So you can kind of create your own module, and that's what we're not creating any modules here. So I've talked about creating modules and drivers in the past, but we're just going to be literally doing this work in main.c. So. But one thing I would say is make sure that you're looking for a viable driver or module first. Many a times that somebody else in the community has probably already created it, so you just want to look for it and see if you can implement, or you can kind of add it to your WES manifest or import it somehow into your project. So yeah, don't reinvent the wheel if you don't need to. We'll start off with the configuration, like I always kind of go through. You need to make sure that I2C is enabled. If not, you're going to have problems. Here is an example. I removed one device from this just so you can see it's a little bit bigger. The most important parts are the parts that I highlighted in red there. So you just need to make sure that your I2C device is set status OK. Status OK basically says, hey, this device is turned on, it's ready. At least in the overlay and the device tree. Compatible sets it to whatever kind of module or driver that is defined. And then importantly is the data pin and the clock pin. So at the very least, you're going to need these four things, and obviously setting that node label or whatever it is, I2C 0, I2C 1, or for different platforms, it might be different. So bear that in mind. So we're just going to be accessing the I2C 1 directly versus kind of using a label or something for device accessing a specific device, and you'll see that in a second. So we're getting this device. We've created a construct of the device. It's just a pointer, and that gets kind of set up at compile time. So if you're ever getting weird compile errors related to device tree, most likely it's not correct. In this case, I'm getting using the DT node label, and I'm setting I2C 1. So that part right here, that's probably the most important part to getting the I2C device. Is I'm literally putting I2C 1, that's the same name of the device, back in the overlay here. So we're getting the device, and then during runtime, we're making sure that it's not null and its device is ready. So those are kind of the things to do before you actually start using the device. And most of the time, if not all of the time, it's going to be ready and available for you to use. So unless you're doing something weird in your code. So then we can actually start immediately using it. So I'm reading the who am I register in the LAS2DH, and we're setting so that first parameter is the actual device pointer to the device. The second is the address of the device. The third is the register address on the actual device. So you have the I2C address and then the register address, and then a pointer to the data that we're going to be reading out. So in this case, it's just one single byte. So I just created a byte, called it who am I. Now for writing, it's very similar. We're giving it the address, the register, and then also just the value that we want to write to that register. Again, pretty straightforward. Many of you have done something similar. It's not much to be explained there. We're just kind of building off of what we've seen. Updating, though, is also an interesting one, where you can basically take the address, the register, and then you can set a mask, so a bit mask for that particular register. So register is 8-bit wide. You can set a mask. So I only want to modify bit 2. So you would make 2 as the value, and then you could set the value to whatever you want. You can set it to 0. You could set it to 1. In the case of the value, you can make it even FF or 00 because you're only targeting that one specific bit in that mask. If you make the mask 0xFF, then you're going to hit all the bits in that particular register. So it'll read it, modify it, and update it. To get that value, if you ever want to do it, then you might want to do it manually with a read and then do the modifications and then write it. But if you just want to update it and not really think about it and just update one particular bit or in a specific mask, it could be multiple bits, by the way, you can use this update command. So I find myself using it once in a while. It's handy to know about, and it's a good option. So here it is again, just so you can see. So that you get the address, the register, the mask. And in this case, I'm using the same value for the mask and for the value, because I'm just setting the same bit. So, and here comes the fun ones. Burst read and write. They're very handy for operations where if you're unfamiliar with I2C, you basically write the beginning address where you want to do some writing or reading, and then without sending a stop condition, you can basically write to the next register. So I start at register 0, I write that byte, and then automatically it gets incremented to the next byte and the next byte and the next byte until you're done writing or reading. So this is very handy because you can kind of slurp up everything on the device kind of in one shot, put it into a buffer, and you're done. So this is what it's useful. This is what it's used for. For this particular device, it's actually very useful for getting the XYZ data. For each axis is actually 2 bytes. So you have to take those 16 bits and per register and kind of finagle them after. So, but in this case, I'm writing to register 0 and 1. And I created a register, kind of just a blank value, which is not included here, but I can show it in the code in a second. And I'm just writing to those 2 particular registers. So we start at CTRL 0, control 0, and then it'll automatically increment to control 1, which is handy. And you can see, okay, here it is. You can see right at the top here, I just kind of initialized this guy right here to 0, and then I'm actually reading the contents and writing the contents back. These slides are out of order, but you can see here again, should look familiar at this point, where you have the address, you have the register you're starting at, you have the data structure that you're actually writing the data to or reading the data, and then you want how many bytes you're going to be reading. So I only want 2 bytes. I want to read control 0, control 1, so just using the size of method, and that's that's not runtime. That's actually done during compilation. So sorry, I had a little brain fart there. One thing that's very handy, and I actually was using it and it popped up and I was like, oh, I probably should share this. If you're using VS Code and the C++ C plugin, if you highlight over any of these functions, it will actually give you the parameters and everything, or you don't even have to go to the header file to get it. So I was like, what parameter is what order and what? So this is very handy if you find yourself, I'm like, how do I work with that API? It's probably already got it categorized and searched, and all you have to do is just start typing it or highlight over it. So very handy. I'll show it to you again. I'm kind of leave this up, but cool little tool without having to leave VS Code to figure out how to use the API. So demo time. So I'm gonna run over to VS Code, and hopefully this is the right one. I'm going to do that, and I gotta plug it in. And I'm just going to load and monitor here. Should take a quick second. Maybe I can make this smaller so people can actually, oh, it's not going to make it bigger though. I'm going to do this on the fly here. And there you go. So now I'll just open up main, and then we'll go over the where did I put it? Here we go. So at this point, this should look similar. I just basically, in the slides, I just kind of took each step and went through it. So we'll go to the top. I put all the registers. So normally this would be in the, I just took this from the LAS 2DH header file. So in this case, I was just keeping it right here just for usefulness and convenience. And then if you like scroll down here, you can see getting the who am I register, which Mike pointed out, yes, it is 0x33. So we're getting the device first, or just checking for errors, making sure it's good. Reading the who am I register. So we're checking, device here, checking the who am I register here, printing it out, writing the control 0 register, which I'm just writing the default value. The default value is just this guy. And let's see, control, oh, that's a typo. And then updating the one of the bits in the in this case it's the X enable bit for control 1. Again, all right here. And every single time I do it, I'm like checking for errors to make sure there's nothing wonky going on. And as long as your hardware is solid, you're not really going to run into any errors. You might run into errors if you're doing these things outside. So I would pick one loop in your code that's going to be doing all the reading and writing to I2C. It's just going to make your life a lot easier. I2C is not thread safe, so you're going to have to pick a thread and stick with it. In my case, most of the time, I'm using the main thread. So just bear that in mind. Setting that guy, doing the burst read, again, reading those control 0, control 1 registers, the same ones I've been manipulating the whole time. Printing it out, and then doing a burst write, which I'm just writing back the same things I read. So if you go down here, you can actually see like every step of the process. Let me see if I can make it. And I'll make this bigger. But you can see the output here, the printf statements. Who am I? 0x33, like Mike said. And then control 0, we're setting default. Control 1, we're enabling the X bit. So every time it's successful, I'm just printing out the progress. Just as an example, just for anybody who wants to check it out, who wants to do something like this themselves. Well, there you go. All this code is available on GitHub, and I put the link in the description box below. And if it's not there, I will add it, but I'm pretty sure it's in the description box. So that is it. So yes, Zephyr gives you the same affordances that you can use, that many of you are used to in other SDKs. Direct I2C access without diddling around with drivers. I still highly recommend, if you can get something in where it's written as a driver, do it that way. But this is also an option, especially if you're just doing bring up or testing or something. That is definitely an option. And let's see. And then I kind of reiterated just like not really recommended for like long term for code that you might want to reuse. Generally, drivers you want to like kind of create them and put them in their own little bucket so they can be updated or changed, and other people can use them. A lot of the drivers I've written, I kind of put them up on GitHub and allow people so they can search for it. Zephyr, XYZ device. So hopefully it would help somebody else in the process, because not all these devices are in Zephyr tree. And it's kind of a process to add it to the main tree. So it's just like, why not make it available? Because sometimes you might make a driver, but it's not going to have all the features and flags and all that fun stuff that other people might want. So, and then you can see like the things that we've done. We've done reading, writing, updating, and then all the burst operations, which include writing and reading. So. And I'll jump into some questions. Looks like we're really rolling here, 16 minutes. But I did see there's some questions from Yagaya. Thanks for coming back, by the way, Yagaya. It's great to see you. Early question, does it mean accessing I2C is within user space compared to kernel module space access? I don't think there's really a context of user space versus kernel space in Zephyr. And folks can correct me if I'm wrong. For certain devices, for instance, for the NRF9160, for anything that's the Cortex M33 or newer, they do have kind of the peripheral protection, the ARM, whatever, trust zone, which provides kind of some, which basically kind of does this where it only allows certain peripherals to be used in an application. But for other devices, STM32, anything Nordic NR52 or younger or older, those don't really have this. Like, you're basically running bare metal code. The kernel is just helping move threads around and do things in the background if you got logging turned on or things like that. So there's not really any difference, really. You're going to be you're running it with privileges, essentially. So I hope that helps. And then Veroxin, the inspiration for this question. So thanks for being here. Does an NRF Twin use the PCF device, or does it create its own driver? There's no driver, or I should take a step back. So the PCF device is a driver that I wrote. I added that device in there. You can look at the NRF9160 Feather common.dts device tree bindings, and it'll give you like all the devices that are attached to that I2C bus. I'm not using that at all. Right now, I'm actually talking raw data right to the I2C bus, just writing and reading bytes from specific addresses that I specify in that I2C. So if you want to, you can look at the PCF, that RTC timer driver that I wrote. I'll see if I can add that to the description after this. But you can see I'm using this I2C API within that driver. But that driver requires turning on some other features, actually turning on in the configuration, like turning on the PCF driver itself. So not the same. That's where the confusion is a lot of times with overlay is, oh, I put it in the overlay, I can just start using it. It's like, no, the overlay is like the skeleton of your device or your project and how you want to use it. And it's kind of like the switches, like on and off. But anything where the code or the smarts that's behind it is all done with configuration and then also in modules or whatever. So they're two pieces of the pie, and they need to be put together for you to use any type of driver or anything, any module or things like that. So I hope that helps. And it's confusing, like especially if you're starting from scratch, if you're just starting with Zephyr now, it is a little confusing. Like, what the heck is this overlay thing? And like, why can't I just turn GPIO on and off directly? Like, why? Or like, for instance, this I2C. this I2C API. It's like, why can't I just read and write bytes, man? I just want some bytes. Come on. But it's good for good reason, and a lot of the reason is you can reuse it and share it and improve upon it outside your project, and it just kind of makes the code modular and reusable. A lot of software engineering buzzwords here. So, but once you start playing with Zephyr some more, you'll see the advantages. And like, this is someone talking with like 2 years of diving deep into Zephyr, and it takes like a while to get up to snuff. And the main point of these live sessions is to help you guys and girls kind of get up to snuff faster, because some of the times it's just like, how do I do this? This documentation is crazy. Like, it's missing. It's like, doesn't exist. So, hope that really helps. And, yeah, that's about it for today. It looks like I'm done here. No more questions. Yeah, Zephyr is definitely a little confusing from scratch, what I'm getting there. I'm glad you're sticking in there, because it's pretty rewarding once you get to the point where you have code that's working. And you're like, oh, I just want to switch processors. It's like, oh, just change my board file, or change my board. It's like cool. So once you get there, it's like, okay, I get the idea. So yeah, thanks for being here. Looks like we got 22 minutes. Thank you. Would you be able to do, so another question from Voxerin. Would you make a video on downloading and parsing JSON file? I'll add it to the list. Let's see what I can do. Zephyr has some good support with JSON. In particular, CJSON is one library. And I think there's another library where you can basically take a JSON blob and it will parse it into an existing C struct. I know the guys from Goliath, where they did a presentation on that particular piece of code. I didn't even know it existed. So that might be interesting too. But I'll see what I can cook up. I'll add it to my list. There's a lot of stuff to go through. I want to do these like twice a week, but things are just so crazy right now. But I appreciate all the suggestion. I'm gonna totally add that right now. Yeah, it supports tests, and that's one thing I haven't really got into. I've never really done a lot of tests, like unit testing and things like that in C. It's kind of difficult. I know that, again, the Goliath folks are doing a lot of emulation, or creating these kind of emulated NRF52 and NRF91 devices and kind of doing things on them. I haven't played enough with them to be like, this is how you do it. But it's something that I do want to play with in the near future to kind of get going, and especially like tests. It's just, those are so important, and it's just for sanity. Like, you can set that up with your build, or you can just it can be a step before you build your Zephyr project in a CI, like using GitHub or whatever. So very handy. It does exist, but I will add that also to the list. I think it's already in the list, but yeah. A lot of cool stuff in Zephyr, and it's like, this is barely scratching the surface. So let's see. And other questions, comments? Today saw Zephyr Sports test as well. Yes. And then I got confused when using the CJSON library or the Zephyr JSON library. Yeah. So the Zephyr JSON library, I think, is the one that I was mentioning, was the one where it will parse it and put it into automatically kind of suck it into a struct. It is a little hairy, and it takes a little bit, like, I preferred using QCBor, which is another library that's not it's not Zephyr specific, but there are some little shims you can put in to get it working, and it's just so easy to use. You just like, this is creating this payload, XYZ, and then you can decode it on the other end too, which is really nice. But all these other libraries like CJSON work in a very similar way. So once you kind of get one, you can kind of use it in other ways. So, but that's it for now. I really appreciate y'all being here on this Thursday, Cinco de Mayo. Hope you have a great day.